So we're just discussing the number of signals you might expect to have from a particular compound. And that's where you want to look at symmetry, and we want to look at rotation and reflection and use our shortcuts to figure out how many signals to expect. Then the next question is, where are the signals going to show up on the x-axis? And that is the chemical shift. Now, in most NMR solvents, 1% TMS, tetramethylsilane, is used as an internal standard, and the chemical shift is found using this formula. The observed shift from TMS in hertz divided by the operating frequency of the instrument in hertz. So for benzene on a 300 megahertz instrument, the chemical shift would be as shown here. The hertz of the signal is different in different instruments, but the shift relative to TMS is constant. So regardless of the strength of the instrument that you're using, the chemical shift that you will get will be the same. The chemical shift is a dimensionless number because the hertz units cancel out. But the units for the chemical shift are often given as parts per million, which simply indicates that the signals are reported as a fraction of the operating frequency of the spectrometer. And most signals appear between 0 and 10 ppm. On the last slide, the chemical shift was 7.27 times 10 to the minus 6, so that 10 to the minus 6 is where the parts per million comes from. So then that would just be 7.27 ppm. There are a couple terms that are used that are artifacts of early NMRs that analyze samples at a constant energy over a range of magnetic field strengths, and now we do it the reverse way. But the low field strength term is called downfield, and the high field strength term is called upfield. So downfield refers to the left portion of the spectrum, whereas upfield refers to the right portion of the spectrum, the portion closer to 0. Signals that show up downfield are D-shielded. You can think D for downfield matches the D of D-shielded, and signals that show up upfield are shielded protons. So shielded protons required a stronger external magnetic field to be excited at the same energy as D-shielded protons. So shielded protons have a smaller magnetic force acting on them because the electrons that are surrounding those protons have, in the presence of the external magnetic field, their own induced magnetic field, which is opposing the external magnetic field, shielding that proton from experiencing the full extent of that external magnetic field. And as a result, there's a smaller energy gap between the low and high energy spin states, and therefore it requires less radio energy to flip the spin states. And therefore those protons are going to show up upfield, versus protons that are D-shielded, which means they experience more of an external magnetic field, which means they require more energy to flip their spin state from the alpha to the beta, and those will show up downfield in this area. In shielding, electrons shield a particular hydrogen atom from experiencing the full force of the external magnetic field. Can you think of a real-world analogy for shielding? Brainstorm and put your thoughts in the chat. And there are tables of chemical shift data that help us to know where to expect certain protons to show up. So protons can be shifted downfield when they are adjacent to electronegative atoms. So if we look at methane here, it shows up at 1.0. So the hydrogens in red show up at 1 ppm. By adding a halogen iodine, that shifts those hydrogens to 2.2 ppm. If we add the more electronegative bromine atom, they shift to 2.7. If we add the even more electronegative chlorine, they shift downfield to 3.1. And if we add the very electronegative, the most electronegative element on the periodic table, to fluorine, then they show up at 4.3 ppm. So notice that the hydrogen signal shifted further downfield when an electronegative atom was attached. And that's because it is pulling electron density away from those red hydrogens, which essentially is de-shielding it. If we look at this series here, we see that by adding additional electronegative atoms also gives the same effect of moving the shift further downfield. In addition, the closer those hydrogens are to the electronegative atom, the more they feel that effect. So these hydrogens that are on the same carbon the chlorine's attached to are the furthest downfield. These hydrogens are a carbon removed on the beta carbon, so they aren't feeling the effect as much. And then these hydrogens are far enough away, they really no longer feel the effect of that electronegative atom. So the electronegative atom has an effect, but only over certain distances. To predict chemical shifts, you want to start with the standard ppm for the type of proton. The methyl proton has a standard ppm of 0.9. For methylene, which is just a CH2 group, it's 1.2. And for a methine, which is a carbon with just one H attached and 3 other bonds, it's 1.7. Then you can determine the effect of neighboring functional groups. So if we start with the methylene base ppm of 1.2, if that is next to an oxygen, you can add 2.5 to get to the actual chemical shift of 3.7. If the methylene group, which has a base reference of 1.2, is next to oxygen of an ester, so notice this is of an ester, this would be of an alcohol or an ether, we add 3 ppm to get to a value of 4.2. So these are ways we can estimate the chemical shift. Experimentally, it may differ slightly from our predicted values, but it should be kind of close. And then the effect on beta protons is about 1/5 the effect on alpha protons. So the beta protons would be this proton, these protons, for example, and these protons. If your protons are in a carbon adjacent to a carbonyl, then we typically add 1 ppm to the value. So here that would give us a predicted value of 2.2. The actual chemical shift is 2.4. Here are 2 different compounds, and in the top compound, the ester, there are 4 unique proton signals, and I've labeled them HA, HB, HC, HD. In the bottom compound, there are also 4 different unique proton signals, HE, HF, HG, and HH. What I'd like you to attempt here is to calculate the chemical shift for each unique hydrogen. You could each take one and put your answer in the chat. So what you'll need to do is start with a base value depending upon whether the hydrogen is on a CH3 or CH2 or CH group. And then you're going to look to the tables in the previous slides, and you're going to have to add a certain amount depending on whether they are next to a carbonyl or an oxygen and how far away from those groups they are, because those groups will inductively withdraw electrons, which will have a de-shielding effect. The last topic is anisotropic effects. When electrons in a pi system are exposed to an external magnetic field, they circulate and produce a magnetic field, causing diamagnetic anisotropy. So here is an example. So for example, if you had a benzene ring and the electrons in those pi bonds, there's 3 pi bonds in the benzene ring, are exposed to an external magnetic field, they start to circulate, and that produces its own magnetic field. So as a result, the protons that are here on the outside of the ring experience the external magnetic field plus this induced magnetic field. And as a result, they are further de-shielded by this induced magnetic field. As a result, these protons will show up downfield. So these hydrogens in red are showing up here past 7 ppm. The result of this effect is similar to shielding for protons when they're on the inside of the pi system. So here the protons on the inside of the ring appear at -1 ppm, where the ones on the outside appear at 8 ppm. Here is a handy table of different protons and where we expect to see their chemical shifts. And this is a very useful tool when you're analyzing an NMR spectrum and trying to deduce what type of structure you have. So as a question at the end here, consider cyclohexanone, a 6-membered ring with a carbonyl. Tell me how many signals you expect. In other words, how many sets of chemically identical protons are there? And then tell me for each signal, what do you estimate the chemical shifts to be? That's all. We'll talk about this more in class and do lots of practice problems.